Alright, very good day to you. Today we are looking at chapter 7.2, properties of covalent molecular substance. So I need to look at page number 161, page 161 on intermolecular forces. So it's stated here, molecular forces are the forces between molecules. These molecular forces are 100 times weaker than strong bonds of bonding such as ionic, metallic, and covalent bonds. So before this, we have looked at ionic compounds. We are talking about bonding between metal and non-metal, metallic metal compounds, covalent molecules. When we talk about covalent molecules, we are talking about sharing of electrons or sharing of valence electrons. Intermolecular forces is basically the forces between the molecules, the forces between the molecules. These ionic, metallic, and covalent, and today we are looking at intermolecular forces. And since here covalent molecular substances tend to have a much lower melting and boiling point than ionic, metallic, and covalent network substance because the intermolecular forces are much weaker. A very good example would be water molecules. If you're talking about the bonding within the water molecule, there will be the intramolecular force in the form of covalent bonding. The bonding between different water molecules will be of intermolecular forces. And what this is trying to say here is that covalent molecules and water molecules, they have a much lower melting and boiling point as compared to ionic, metal, covalent network substance, because the intermolecular forces in the covalent molecules are a lot smaller. Just to make it clear, covalent molecular substance is different from covalent network substance. Covalent network substance will be of a very large giant lattice structure, such as diamond. Consists of many atoms in that particular compound, as compared to a simple covalent molecule such as water molecule. Alright, moving on to the next slide. So it's stated here is the weak intermolecular forces. They are broken when a covalent molecular substance is converted from solid to liquid or from liquid to gas. They say when liquid changes to gases, the intermolecular bonds are broken. For example, liquid water changes to gaseous water. The intermolecular bonds holding the water molecules to other water molecules are broken, not the covalent bond. Just to make it clear once again on this slide here, and I will write this on the board. Just give me a second. So let's just say we talk about a covalent molecule. We have H2O, which is your water molecule. If you're talking about water molecule, the bond between one water molecule and another water molecule is the intermolecular force, which is the hydrogen bond. Which means the bond within the water molecule, molecule is not broken. What has been broken is the hydrogen bond itself. Alright, what has been broken is the hydrogen bond itself. If I'm going to draw one more, I'll draw one more at the bottom. Just give me a moment here. So let's just say that you have your water molecule. Let's say this is your oxygen. You have your hydrogen. And based on what we have discussed in class, each water molecule will have 2 lone pair electrons, if you still recall what we have discussed in the last class. So in this case, the bond between this oxygen and I'll use these dashed lines to represent the hydrogen bond. So in this case, you can see that the bond that is being broken is the hydrogen bond, not the covalent bond. So when I'm talking about the hydrogen bond, I'm referring to this. So this bond here is the intermolecular force. So in the intermolecular force is the one that is being broken, but the intramolecular force remains intact. Alright, I'll repeat one more time. So this one here is the intermolecular force, which is the hydrogen bond. As you can see, the bond between hydrogen and the oxygen atom of another water molecule, and this covalent bond is not broken. So within the water molecule, the covalent bond remains intact, but the hydrogen bond is broken. Alright, we are done. I'm moving on to the next slide. Alright, hardness of covalent molecular substance. You see, in general, covalent molecular substances tend to be softer than ionic or metallic substances. These substances are soft because the intermolecular force holding the molecules together are weak. So we have discussed this. We know that the bonding between the covalent molecules is a lot weaker as compared to the bond within the covalent molecules. So it says therefore the bonds between the molecules can be readily broken and the substance can be easily molded, scratched, or crushed. Moving on to the next slide. So electronegativity and polarity. Today we are looking at something new. Here we are talking about electronegativity and polarity. If you still remember what we have done in chapter 1 and 2, we talked about electronegativity. What is electronegativity? It's a tendency of attracting electron. So I'm reading the first paragraph here. This is from your textbook. It says intermolecular forces. The electrostatic attraction is between positive and negative charges in the molecule. It says these charges appear as a result of uneven electron distribution. If you are talking about covalent molecules here, if the covalent molecule consists of different atoms, most likely there will be a difference in that electronegativity forces. So you say electronegativity is a key factor that determines the electron distribution in diatomic molecule. Diatomic means there's two atoms within the molecule. Electronegativity is a tendency of an atom in a covalent bond to attract electrons. Electronegativity increases from left to right across the period and decreases down the group. Bear in mind, electronegativity is present in all compounds. If you're talking about ionic compounds, based on what we discussed before at the start of the year in chapter 3 and 4, metallic compound in chapter 3 and ionic compound in chapter 4, metal compounds in chapter 3. When we talk about ionic compounds such as sodium chloride, which is the salt or table salt they use at home, we know that the reason why you have the ionic bond is because the tendency of sodium releasing electron is very high and the tendency of chlorine accepting electron is very high. So which means the electronegativity of sodium is very low and the electronegativity of chlorine is very high. Because of the difference in the electronegativity, there's a reason why we have the electron transfer diagram. Electron is being transferred from sodium to chlorine. But coming back to this here, when we are talking about covalent molecules, you're talking about sharing of electrons, which means that if the electronegativity of one or the other atom is a lot higher, which means that the electrons will start to move from this atom to another or from the other atom to this atom, as you can see here. So move on to next. So based on this periodic table, you can see they're moving towards the right of the periodic table. You can see, moving towards the right of the periodic table, you can see that the electronegativity value is a lot higher on the right hand side of the periodic table, which means that there's a higher tendency of attracting electron. If you go down the group, you can see electronegativity value decreases because its tendency of attracting electron is a lot smaller. So this is what you can see. So the trend here is going across the period, electronegativity value increases, going down the group, electronegativity value decreases, which means that if you have, let's just say, H2 or water molecule based on what we have discussed, we know that hydrogen is here, it has electronegativity 2.2, oxygen has electronegativity 3.44. So there is a difference on electronegativity value here. So most likely that can affect the polarity of the substance, which is what we're going to discuss on the next few slides. So I'm moving on to the next slide. So you can see here, this is talking about diatomic molecules. We have non-polar, we have polar diatomic molecules. Non-polar means that there is no polarity. The polarity is zero. There is no charge. So what are the conditions that we need for it to be non-polar? As you can see here, there is a trend, and the trend that you see is that all of them here consist of the same atom. So if you have chlorine, oxygen, hydrogen, and nitrogen, chlorine is Cl2, oxygen is O2, hydrogen is H2, nitrogen is N2. The bonds with an equal distribution of the valence electron are said to be non-polar because there is no charge on either side of the molecule. If you look at this molecule on the right hand side, you can see that this is a fluorine molecule. The electronegativity value of this fluorine and this fluorine is the same, which means that this is now a non-polar molecule because of the symmetric distribution of electron. Alright, you have to be very clear. For a molecule or for a covalent molecule to be non-polar, the electronegativity value of both atoms have to be the same, which means electrons are being shared equally on both atoms. If you have a polar diatomic molecules, most likely it's because the electronegative value is different between the atoms. There are also other reasons as well, but in general, we can say that if the electrons is not being distributed evenly within the molecules, then you will get a polar molecule. If the electrons are shared or distributed equally, then it is most likely, or in this case, it is a non-polar covalent molecule. So moving on to the next slide. Polar diatomic molecules, based on what we have discussed as well, a very good example here is hydrogen fluoride, HF, hydrogen fluoride, HF. We know the electronegative value of fluorine is a lot higher than electronegativity of hydrogen, which means that there's a higher tendency of fluorine attracting electrons from hydrogen. So you see here, if the covalent bond is between atoms of different elements, then the electron will stay closer to the most electronegative atom. In this case, will be fluorine. So you will have hydrogen fluoride. You see, a fluorine atom is more electronegative than a hydrogen atom. Therefore, in the hydrogen fluoride molecule, the electrons tend to stay closer to the fluorine atom. This imbalance in the electron distribution means that the fluorine atom is negatively charged and the hydrogen atom is positively charged. Because of the difference in the electronic value, we know that there's a high tendency of fluorine attracting electron, in this case from hydrogen. I'll show you diagrams, I'll show you a few diagrams of how polar molecules looks like. Just bear with me, moving on to the next. So hydrogen fluoride, once again, is the fluorine atom has a partial negative charge and the hydrogen atom has a partial positive charge. The separation of the positive and negative charges is known as an electric dipole, or simply as a dipole, as they have two oppositely charged poles on each side of the molecule. Hydrogen fluoride is a polar molecule because it has a permanent electric dipole created by the different electronegativities. Electric dipole means that it can be partial positive, partial negative. Bear in mind, this is not an ionic compound. This is not an ionic compound. They do not form charge at the end of the sharing of electrons. What this is trying to tell you is that if the atoms consist of different atoms or atoms with different electronegative value, most likely the distribution of electrons will not be equal, which means that one side of the atom will become partial positive charge and one side of the atom will become partial negative charge. So you get what we call a permanent electric dipole created by difference in that electronegative value. So moving on. So polarity of any covalent bond can be compared by examining the difference in electronegativity of the atoms. As the difference in electronegativity of two atoms increases, the covalent bonds formed between the atoms increases in polarity. In other words, it becomes more like an ionic bond. But it is not an ionic bond. Just to be clear on the last part here, it is not an ionic compound. It is because of the sharing of electrons and the distributed electron is not equal on both sides of the atoms. It starts to behave like an ionic compound, but it is not an ionic compound. Moving on to the next slide. So this is an example, a question. Compare the polarity of covalent bonds in hydrogen fluoride and carbon monoxide. You know that electronegative value of hydrogen fluoride or hydrogen fluorine here is different. Carbon and oxygen is different. You can see that there will be difference in electronegative value. Hydrogen fluoride will be 1.78, carbon monoxide will be 0.89, and we know hydrogen fluoride is more polar than carbon monoxide. So what you need to do here, you need to go back to the table that I've shown you in the last few slides, and you need to calculate the polarity of the covalent bond. We will discuss this in class. So make sure that you do this question here. What you need to do, you need to have the electronegative value of nitrogen, electronegative value of oxygen, and you deduct them. The same goes for hydrogen chloride. Electronegative value of hydrogen, electronegative chlorine, and then you can find the difference in electronegativity value. Moving on to the next slide. So polarity of polyatomic molecules. We're almost there. It says determine the polarity of molecules with more than two atoms. So it's more complicated, and we'll discuss why they are a little bit more complicated. Polyatomic molecules consist of more than two atoms in general. So diatomic molecules consist of two atoms. If you have polyatomic molecule, it consists of more than two atoms. There's a few atoms together. This is the polarity of polyatomic molecule depends on the share of molecule as well as polarity of covalent bond. In general, symmetrical molecules are non-polar, asymmetrical molecules are polar. I'll show you a few examples, but in general, what this is trying to tell you, even though you may have a molecule that consists of different atoms or the atoms of the same type of the same element, but you have to look at the structure itself, the 3D structure. If the molecule is symmetrical, it will be non-polar. If the molecule is asymmetrical, it will be polar in general. That is the trend of a polyatomic molecule. So non-polar molecules, once again, they are symmetrical. If you're talking about polyatomic molecule, if it's non-polar, it has to be symmetrical. So an example here will be a methane. This is a methane. We did discuss this in the last few lessons. So I read this for you. In methane, the carbon atom is slightly more electronegative than the hydrogen atoms. Therefore, the carbon atoms attract the electrons more strongly than each hydrogen atom and has a partial negative charge, leaving hydrogen with a partial positive charge. However, the methane molecule is a perfect tetrahedron. We talk about it being tetrahedral, how it has a bond angle of 109.5. It is therefore symmetrical. The symmetry of molecule means that individual dipole of the covalent bonds cancel each other perfectly. The result is a molecule with no overall dipole. As you can see in this structure here, there is no dipole, means the dipole is 0. And it is non-polar because it is symmetrical. You can see that this is and these are the angles that represent how the bonds fold. How the electrons falls in that particular bond. You know that is falling from partially positive to partially negative here. So even though you have individual dipole, yes, there is a difference in the electronegativity value, but because it is a symmetrical structure, and if you spin this, it's a 3D and it's symmetric. If you try and divide it into half, and I'll show this to you, if you try and divide into half here, or here, or the other side, it will be the same on both sides. So which means that in this case, even though it has individual dipole, but it's distributed symmetrically or equally on all sides, the overall dipole will be 0. It is a non-polar molecule. So polar molecule means that it is asymmetrical. If it's asymmetrical, means that the individual dipoles or the covalent bonds do not cancel each other. This results in a net dipole, making the overall molecule polar. The chloromethyl. So chloromethyl structure here is CH3Cl. So what chloromethyl is telling us is that there is a difference in electronegativity value. As you are probably aware, chlorine atom is more electronegative than the carbon atom. Therefore, the chlorine atom attracts electrons from the carbon atom, and the carbon atoms attract electrons from the hydrogen atoms, as you can see here. As a result, you do have a net dipole. So this is moving outward. The individual dipole is moving outward. You get a net dipole that is moving from partially positive to partially negative, moving outward. So this chloromethyl structure, CH3Cl is an asymmetrical structure, which means that it has an overall dipole. It's the overall of a net dipole moment. Moving on. So, if we are going to summarize this, formaldehyde, which is metana, we did discuss metana in the last few lessons, CH2O, metana, CH2O, you have 2 single bond and 1 double bond, is asymmetrical, is polar. Carbon monoxide, alright, with the difference between carbon monoxide and water molecule, you still remember water molecule has that 2 lone pair electrons, and it's actually, it still have the individual dipole, they do not cancel each other. I'll show you in the bottom example here, but carbon dioxide here, you can see that the dipole moment here will be 0. How do we get 0? I'll show this for you. Just give me a second. Here, you can see that partially positive always goes to partially negative. So in this case, they do cancel each other off, which means because it's a symmetrical structure, the net dipole moment here will be 0. So it's a non-polar molecule. So moving on to the next one, we do have tetrafluoromethane. Tetrafluoromethane is CF4, is symmetrical. If it's symmetrical, it has to be non-polar. So tetrafluoromethane, symmetrical, non-polar, done. Water molecules, it has a net dipole moment, and how it works here, let me show you. Because in this case, you remember it has that 2 lone pair electron, and this dipole is flowing from partially positive, partially negative, so it does have a net dipole moment. It's asymmetrical, it's polar. Ammonia, it does have 1 lone pair electron in that nitrogen atom, and we know that ammonia here is contributing outward, is asymmetrical, is polar as well. So it's contributing outward and is asymmetrical, which means it's polar. So in general, there's 2 main factors here. Number 1, you have to see whether there's difference in electronegativity value. If the electron value of both atoms is the same, most likely is non-polar. If the electronegativity of both atoms are different, then most likely it will be polar. That only applies to diatomic molecule. If it's a polyatomic molecule, you have to look at whether it's symmetrical or not symmetrical. If it's symmetrical, most likely it's non-polar. If it's asymmetrical, most likely it's polar. Alright, so think about that for you to determine whether a molecule is polar or non-polar. Moving on to so, solubility of polar and non-polar substance. It says here the polarity of a molecular substance has a significant impact on its solubility. In general, substances that are polar tend to dissolve in polar solvent. Non-polar tend to dissolve in non-polar solvent. If you try and put water and oil together, you know that it doesn't mix because light dissolves light. So, polar molecules and water molecules do not dissolve in non-polar substance such as lipid or oil, and that is the main difference. Alright, so if you try and dissolve, let's just say another polar molecule such as ammonia, for example, as that one lone pair electron, ammonia can dissolve in water, but it can't dissolve in non-polar substance. Alright, bear in mind, there may be cases like, let's just say you talk about carbon dioxide gas. Carbon dioxide gas is non-polar because it's symmetrical. You may say that it dissolves in water, but technically say it doesn't dissolve in water. You may find carbon dioxide gas in water molecule, but it's usually present in very small quantity or amount because it does not dissolve in water. So once again, light dissolve light. Polar molecule dissolve in polar substance or polar solvents, and non-polar substance dissolve in non-polar solvent.